Hi everyone, in this video we're going to begin talking about the real zeros of a polynomial function. And so we're going to begin by using the remainder and factor theorems, and then in the next videos we'll cover these other objectives. Okay, so first let's talk about what's called the division algorithm for polynomials. And essentially what it breaks down to is this statement down here. If we take two polynomials and we divide them, okay, that's f divided by g, then what we get is a quotient. So this part here is a quotient plus the remainder over the divisor. And this is what happens when you divide regular numbers. It's the same concept using long division. Let me just show you what I'm talking about. So let's say I wanted to divide some number by another number. Okay, so I have 4 goes into 51. We're going to just do this really quick with long division. And this same process works with dividing polynomials as well. Okay, and so I'm going to go 4 goes into 11 twice, and then I have a remainder here of 3. And so what I can say is that 51 divided by 4 is 12 plus 3 over 4. So I have my original dividend, my divisor, and then the answer is the quotient. This is the quotient plus the remainder over the divisor. Okay, so the same thing happens with polynomials. So we have our quotient here, quotient plus the remainder, I'll just abbreviate, remainder over the divisor. And the other way to write this is that our original polynomial that we divided, which is called our dividend, if you want to rewrite that, it can be written as the quotient times the divisor plus the remainder. So let me show you that with the numbers really quick. And so if you understand this concept with the numbers, then it's the same thing with our polynomials. So what this says is I can take my original dividend and I can write it as the quotient times the divisor plus the remainder. And if you verify this, this is 48 plus 3, which is 51. So that's our division algorithm for polynomials. Okay, so here is the first theorem, our remainder theorem. And this just says if we have a polynomial f and it's divided by this factor x minus c, then the remainder is actually f of c. So this is a pretty interesting theorem, and let me just rephrase it for you so it makes sense. So if you take your polynomial, whatever this is, you divide it by x minus c, then you're going to get some answer here, the quotient, and then the remainder, the leftover part. So remember we have our plus our remainder over our divisor. The leftover part right here is the same number you get if you plug in c back into the function. Okay, so let's go ahead and work this out so you see what happens with actual values. So find the remainder using our theorem for this function if we are going to divide by two different factors. So x minus 2 for a is the first one. So we're going to use polynomial division. I'll show you the long way, which is going to be like that. But then also we can just use our remainder theorem. So let me do the division the long way really quick and then prove to you that our theorem works. Okay, so I'm going to set this up as my long division, putting a placeholder for the x because there's actually no regular x terms. I'm going to divide by x minus 2. So let me just go through it really quick with you. You cover up, think of covering up this minus 2, and you're thinking to yourself, okay, x times what equals x cubed? And so that would be an x, let me change colors, that would be an x to the second power. Okay, once you determine that, then you multiply by the whole divisor. So x times x squared times x is x cubed, x squared times negative 2 is negative 2x squared, and then you subtract this whole thing. Okay, so when we subtract it, that's going to be 0 here, and that becomes negative 3x squared, and then you repeat. Okay, so let's go ahead and change colors again real quick. So now you ask yourself, x times what is negative 3x squared? And that would be negative 3x. So if you multiply, that's negative 3x times x, negative 3x squared. Negative 3x times negative 2 is positive 6x, and then we will subtract. Okay, so that's going to be 0 right here because those get added. And then if we subtract this, this becomes negative 6x. And one more time, bring down that negative 6. And let's do this one in purple. So we have x times what is negative 6x, and that's going to be negative 6. So if we multiply, negative 6 times x, and then negative 6 times negative 2 is positive 12. And I'm running out of room, but hopefully you can still see it, so I'm going to subtract that. That's going to be 0. And then negative 6 take away 12 is negative 18. So this is the remainder. So we got our remainder the long way. Now let's just use our remainder theorem, which states that if I'm dividing by this factor, x minus c, then my remainder is just going to be f of that number, f of c. So for us, it's going to be f of 2. So we're just, all we're going to do is plug in 2 to the function. And based on our long version of doing this, we should get a negative 18. And so we do. So just plugging this in, this used to say x cubed in our function, minus 5x squared minus 6. Simplifying that, we do in fact get negative 18. So the remainder theorem, if we ever want to know the remainder, is much quicker than actually working out the division. Alright, now let's do this again with the other one, x plus 4. So the only difference on this one is that you have to rewrite the divisor. So our divisor needs to be of the form x minus a number, because then that number goes into our function to give us our remainder. And so this doesn't have a minus, this x plus 4, so you need to rewrite it with a minus sign. So if I rewrite it with a minus sign, then it's x minus negative 4, so this is the number c that we're looking for. So that's what we're going to plug into our function to get our remainder. So if you plug in negative 4, don't forget your parentheses, because it makes a difference. So if you plug in negative 4 into your function, the original function, and simplify, you're going to get negative 150. So that's the remainder when we divide by x plus 4. Okay, so one last theorem for this part of learning about our zeros for our polynomials, and it's the factor theorem. So this theorem says that if we have our polynomial and x minus c is a factor of our polynomial, if and only if f of c equals 0. Okay, so what this means is if we can separate it into these two statements, and that's because this says if and only if. So that means that I can start with the first part of the sentence and it implies the second part and vice versa. So that's why there's two statements here. So the first one here, if f of c is 0, meaning when we plug c into our function, if we get 0 as the answer, that means that x minus c, and the way you're going to see it is going to look like parentheses, x minus c like this, that's actually a factor of our polynomial. And equivalently, if we know that x minus c is already a factor of our polynomial, then that tells us if we plug c into our function that the answer is 0. Okay, so quick reminder of what it means to be a factor. So what this is saying is that when I have my polynomial and I break it apart with multiplication, and it could have quite a few factors, but let's just say there's 2 factors, then we're saying that one of them is x minus c. And we've seen quite a few of these ideas of factoring in the past, so let me just briefly remind you. Let's say you had this polynomial x squared minus 9. This one factors as x minus 3 times x plus 3. And so that's what I mean by factors. Factoring means you separate with multiplication. And so this theorem is talking about this as one of our factors, multiplying together with other factors to equal our original polynomial. So there could be 2 factors, there could be 3, or so on. Okay, so let's go ahead and use this theorem. So determine whether the function has the following factors. Okay, so we have our f of x, and we're going to work on x minus 2 as one of the factors. Okay, so using our theorem, it states that if this is in fact one of our factors, then if we plug in c into our function, the answer should be 0. Okay, so that means x minus 2, the 2 is c. And so if c is 2, we're going to just plug that into our function, and if the answer is 0, according to our theorem, then x minus 2 is a factor. And so if you plug that into the function, which was x cubed minus 2x squared plus 3x minus 6, if you plug in 2, you're going to get 0, which means yes, that was in fact one of the factors of our polynomial. Okay, so just to verify with you so that you understand, you could do this a long way. This is a third degree polynomial, so it's a little bit trickier to factor. But let me just factor it for you real quick, and you'll see that if we didn't have this theorem, then we could still verify x minus 2 was a factor, but the theorem made it much faster. So I'm going to factor this one by grouping. Not all polynomials are able to factor so well like this, but this one does. So if I factor by grouping, the first two terms share an x squared. So if I take that out, I'm left with an x and a minus 2. The second two terms share a 3. So if I take out a positive 3, I'm left with an x minus 2. And then if you notice, these are the same. So I'm going to factor that out to the front. And what's left over is going to go in the second factor. And so look, if you see it, this is exactly what we just verified, that x minus 2 was a factor of our polynomial. It multiplied by something else to equal our entire polynomial. And if you still didn't believe it, you can FOIL it back out and make sure you got where we started from. Okay, so let's do one more. Okay, so this one is to find out if x plus 1 is a factor, but remember, like our previous example with the remainder theorem, we have to rewrite this so that it's x minus a number c, so we can identify c. So if you say x plus 1 and you change that to a minus sign, then that means c is actually negative 1. And so if we can figure out that f of negative 1 is 0, we would know that this is going to be a factor, x plus 1 of our polynomial. So f of x was x cubed minus 2x squared plus 3x minus 6. And so let's plug in negative 1. And so we'll get negative 1 cubed minus 2 times negative 1 squared plus 3 times negative 1 minus 6. We're going to get a negative 1 here. This is going to be positive 1 times negative 2. So negative 2 minus 3 minus 6. So this is negative 12, which is not 0. So no, this is not going to be a factor of our polynomial. Let me show you the long way, this time with synthetic division, to also show you that this is not a factor. So if you've never seen synthetic division, it's very much like long division, but you just leave off your x's in this case. So this is like saying 1x cubed minus 2x squared plus 3x minus 6, but we just leave those variables off. And then what you do is you bring down the 1, and then you start multiplying by your divisor. So negative 1 times 1 goes here, and then you just add those. So negative 2 plus negative 1 is negative 3. And then you multiply again. Let's change colors. So negative 1 times negative 3 is 3. And then you add those, and you get 6. And then you do that again. Negative 1 times 6 is negative 6, and you add those, and you get negative 12. And so because this is the remainder right here, so if this is not 0, then you know that this was not going to go into one of your factors. So we just used our factor theorem, but also proved it using synthetic division, that when we rewrite this polynomial, it's not going to have a factor of x plus 1. Okay, so that's it for this video. We just talked about our two theorems, remainder theorem and the factor theorem. And then in the next videos, we'll start talking more about the real zeros of polynomials and get into what's called Descartes' rule of signs. Okay, see you soon.